right, in the last video we learned this new topic called implicit differentiation, which doesn't really involve a whole lot of new concepts, but can be kind of tricky when you're actually getting through some of the problems. So I thought what I'd do in this video is just a bunch of examples. We're given equations, and in each case we're supposed to determine dy divided by dx, aka y prime. The way we're going to do that in each case is we're going to take the derivative of both sides of the equation. So in this first one I have that xy equals the natural log of x plus 1. Therefore, the derivative of xy must be the same as the derivative of the natural log of x plus 1, which kind of sets up two different problems, right? One on each side of the equal sign. Over on the left, it'd be nice if you saw the product rule in here, because I have something, x in this case, times something else, y in this case. So to take the derivative of a product, I take the derivative of the first thing, x in this case, and multiply that by the second thing, y, and then I add to that the derivative of the second thing, the derivative of the y, times the first thing, the x. On the right side of the equation, hopefully you can see a chain rule. The outer function is the natural log of all this stuff. The inner function is all this stuff. So when I take the derivative using the chain rule, I'm going to first take the derivative of the natural log part. That gives me 1 divided by x plus 1. But then I'm not done. I have to multiply that by the derivative of x plus 1. Back over to the left side here, the derivative of x. X is a variable. Its derivative is just equal to 1. So I get 1 times y. Plus the derivative of y, be a little bit careful. We treat x's differently than we treat y's. Y's are functions, and their derivative is y prime. You can either write dy over dx or y prime. I'm going to write y prime. Save a few characters, I guess. And then I have to multiply that by this x. My left side is completely done. No more d over dx symbols. On the right side, I got 1 over x plus 1 times the derivative of x plus 1. But the thing about the derivative of x plus 1 is it's pretty easy, right? We take the derivative of x, which is just 1, and we add to that derivative of 1, which is 0. At this stage, I'm completely done with derivatives. I guess I can clean things up a little bit. I have all these extra 1s and 0s that I wrote kind of unnecessarily. I got y plus y prime x is equal to 1 over x plus 1. The calculus is done, but what I need to do is solve this for y prime, because that's what I was asked to determine. Get this y prime all by itself. How would you do that? Maybe subtract y from both sides. That gives me y prime x equals 1 divided by x plus 1 minus y. And then you might think to divide both sides by x, which is totally fine. You could do that, but that'll kind of introduce fractions inside fractions. So maybe rather than think about it as dividing both sides by x, think about it as multiplying both sides by 1 over x. So I got 1 over x times 1 over x plus 1 minus y. Y prime is all solved for. You could be done right here, or you could get rid of the parentheses if you felt like it by making it 1 over x times x plus 1 minus y over x. I don't know that this is any cleaner or prettier or neater or more simplified than what you have up here. Any of these answers are totally fine. We were asked to determine y prime. We've solved for y prime. We're done. Let's do another example, maybe a slightly more complicated example. Things over here are going to start out the exact same. We're going to take the derivative of both sides of the equation. So I got the derivative of xy cubed equals the derivative of x plus y. Start with the derivative of the left-hand side of the equation. Hopefully you recognize a product rule in here. So I got the derivative of x, and I want to multiply that by y cubed. To that I want to add the derivative of y cubed, which I will then multiply by x. On the right side of the equation, I got the derivative of a sum. The derivative of sum is just the sum of the derivatives. So I got to take the derivative of the x, and I got to take the derivative of the y, and then I add those two things together. Back over to the left side, the derivative of x is just 1, so I got 1 times y cubed over here. But then this term is a little bit challenging. I've got this x, which I'm going to write first, just so I don't forget about it. And then I have to take the derivative of y cubed. It's not at all obvious what the derivative of y cubed is equal to. In fact, to figure out the derivative of y cubed, we have to use the chain rule. The outer function is the stuff being cubed. The inner function is the letter y, because remember, y is not a variable, it's a function. This is different than x cubed. X cubed is something you can take the derivative of in one step. Y cubed is something that mandates the chain rule, which makes this a little bit more challenging. Taking the derivative of the outside stuff, I got 3 times something squared. That something is whatever my inside function is, left completely alone. In other words, the letter y. But then I'm not done. I have to multiply that by the derivative of that inside function, the letter y. Back over to the right side of the equation, I got the derivative of x, which is just 1 because x is my variable. And then I want to add to that the derivative of y, which remember is not 1 because you treat y's differently than you treat x's. Y is a function, its derivative is y prime. I'm just about done. I just have this one derivative symbol left. 1 times y cubed is just y cubed. To that I want to add the product of x. 3y squared, and the derivative of y. The derivative of y is just y prime, so I could write 3xy squared y prime as this term here. That's equal to 1 plus y prime. At this stage, we're done with the calculus. All that remains is some algebra. However, unlike up here, where the algebra wasn't too complicated because I only had a single y prime in my equation, down here there's two different y primes in my equation, so solving for y prime is a little bit challenging. What you're going to do when you have two different y primes like this is you're going to collect all the terms that have y primes in them on one side of the equation. So maybe I could subtract y cubed from both sides and subtract y prime from both sides, and that would give me 3xy squared y prime, this term right here, minus y prime, the y prime that I get when I subtract this over to the other side, is equal to 1 minus y cubed, because this y cubed moved over here. The reason you want to collect all the terms with y primes in them on one side of the equation is because now you can factor out a y prime from each of those terms, because each of the terms on that side of the equation have a y prime. If I pull a y prime out of this first term, I got 3xy squared left behind. If I pull a y prime out of this term, I have a 1 left behind. So the left side of my equation is y prime times 3xy squared minus 1. Nothing to do on the right side, that's just 1 minus y cubed, and now I'm a step away from solving for y prime. To get y prime all by itself, just divide by all this mess. My final answer for y prime is it's 1 minus y cubed divided by 3x squared y prime minus 1. Kind of tricky, right? I mean, we're not really doing much new in this section, but it just feels a little bit different. Using the chain rule to take the derivative of y cubed certainly feels different than anything we're used to. And then there can be some algebraic challenges as well, like we saw in this example when there were two different y primes and we're trying to solve for y prime. Let's do another one. This might be one you could try on your own. It might not be a bad idea to pause the video here. I got x squared y cubed equals e to the xy power. I'm going to start out doing things the exact same as I've been doing. I'm going to take the derivative of both sides of the equation. Got the derivative of x squared y cubed is equal to the derivative of e to the xy power. When I look at the left side, I see a product rule. I got something, x squared times something else, y cubed. So the derivative is the derivative of the first thing, the x squared, times the second thing, the y cubed, plus the derivative of the second thing, the derivative of the y cubed, times the first thing, the x squared. Over on the right side, I see a chain rule. The outer function is e raised up to some stuff. The inner function is that stuff, x times y. So when I'm taking the derivative, I first take the derivative of the outer function. That produces this e to the xy power. But then I'm not done. I have to multiply that by the derivative of the inside function, the derivative of x times y. Still a lot of work to be done down here. Working from left to right, I got the derivative of x squared, which is just 2x. And when I multiply that 2x by this y cubed, this first term just becomes 2xy cubed. That's not too bad, but this next term is a little bit more challenging. I got this x squared, which I'm going to write right now so I don't forget about it, and then I got to multiply that by the derivative of y cubed. Again, as we saw up here, for the derivative of y cubed, you got to think chain rule. And I know that's counterintuitive. I'm going to use the power rule on this exponent of 3 to bring a 3 down in front. I'm going to leave the inner function, the letter y, completely alone, and I'm going to subtract 1 from that exponent to get this squared. But then I'm not done. I have to multiply that by the derivative of the inner function. The inner function is the letter y. And yes, I know that the derivative of y is just y prime, so it might be easier to just write a y prime in this place, but I'm not going to, because I think by showing the steps this way, it'll help students kind of see that I'm using the chain rule going from this line down to this line. At least that's my hope. On the right side, I got e to the xy times the derivative of x times y. Again, it's a product of two things. So think product rule. Product rule is going to result with two terms, so I better put my parentheses in there. I got the derivative of the first thing, the derivative of the x, times the second thing, the y, plus the derivative of the second thing, the derivative of the y, times the first thing, the x. A few more derivatives left to take. 2xy cubed is all done. I'll leave that alone. Over here, I'm going to write my 3 first just because I think it looks prettier. Then I got my x squared and my y squared. And I got to multiply that by the derivative of y, which is just y prime. Over on this side, I got e to the xy power times the derivative of x is just equal to 1, and 1 times y is just equal to y, plus the derivative of y is y prime. So y prime times x, in other words, xy prime. Good news and bad news. The good news is we don't have any more d over dx symbols, so we're done with the calculus. The bad news is the algebra involved to solve for y prime is a little bit challenging. It's going to end up being pretty similar to what we did up here, where we collect all the terms with y primes in them on one side of the equation. but it's a little bit hard to do that right now because of these parentheses. So what I'm going to do is get rid of these parentheses by distributing the e to the xy power through. So I'll leave the left side completely alone, and on the right side I got y times e to the xy power plus xy prime times e to the xy power. Distributing this e to the xy through these parentheses to get rid of these parentheses. If you can view this as four different terms, 1, 2, 3, 4, and two of those terms have y primes in them, then you're seeing everything that you need to solve for y prime. Just collect the terms with y primes on one side of the equation. Doesn't matter which side. Typically students bring everything to the left, so that's what I'll do. The new left side of my equation would be this term minus this term. The right side of my equation is y e to the xy minus this term, 2xy cubed. At this point, I'm pretty close to done. All the terms in the left have a y prime in them, kind of by design. So I can factor out that y prime, and what I'm left with is 3x squared y squared minus x e to the xy power. I'll leave the right side completely alone, y e to the xy minus 2xy cubed. And now if I want to solve for y prime, all I got to do is divide by this mess to get my final answer. Y e to the xy minus 2xy cubed, all divided by 3x squared y squared minus x e to the xy power. Wow, that's pretty wild. Even if we're not necessarily doing anything new, we're definitely thinking about stuff in a different way. And that makes these problems pretty challenging. This is the last equation that I want to use implicit differentiation on in this video, but I want to redo it one more time to show you a cool little trick that comes into play from implicit differentiation. The fact that we're starting out with equations is kind of a nice thing. In all of the previous sections, we were given some expression to take the derivative of. What's new in this video is we're kind of taking the derivative of an equation, loosely speaking. And the great thing about an equation is you can manipulate an equation, right? If I thought it was useful, I could add 5 to both sides of this equation before I took any derivatives. It won't be useful to add 5 to both sides of this equation before I take the derivatives, but what might be useful before I take the derivatives is to take the log of both sides of the equation. That's what's called a log transform. You have to be a little bit careful when you take the log of both sides of the equation because the log of negative numbers isn't defined. But I don't want to get too far into the minutia with this. We can always just assume that x's and y's are positive numbers, and therefore it's totally fine to take the log of both sides. If I change this equation into the natural log of x squared y cubed equals the natural log of e to the xy before I take the derivative, you might think I'm crazy and you might be like, this is way harder to take the derivative of both sides. There's even more chain rules going on. And that's true, but I'm not going to take the derivative of both sides just yet. What I'm instead going to do is simplify both sides. On the left side, maybe you see a log rule going on here. I have the log of a product, something times something. I can rewrite that as the sum of two different logs, the log of x squared plus the log of y cubed. I've changed the log of a product into the sum of two logs. Generally speaking, addition is better than multiplication when we're taking derivatives, so it's reasonable to think that this might be easier to take the derivative of than this line, or even what I started with way up here. The right side of the equation simplifies even nicer. The natural log of e to the xy power is just equal to xy. There's a few different ways you can come to that conclusion. One is sort of by definition. The natural log is asking you the question, what power do you have to raise e up to change it into this thing? Well, if I want to change an e into this thing, I'd have to raise it to the xy power, because e to the xy is equal to, well, e to the xy. Another way you can think about it is, using the third log rule, I can bring this xy down in front of this natural log, and then all I'm left with is the natural log of e, which is defined to be equal to 1. So I got xy times 1, in other words, xy. What I'm saying is, through one series of logic or another, the natural log of e to the xy power is just equal to xy. The fact that this simplifies so nicely will end up making the calculus easier. You're like, all right, so let's do the calculus. Not yet. The left-hand side can be simplified even more with log rules. I can take this 2 down in front to make this 2 times the natural log of x, and I can bring this 3 down in front to make it 3 times the natural log of y. That's my third log rule. Don't confuse that with derivative rules. This is all just algebra up to this stage. What I've done is I've algebraically manipulated this equation into this equation. And it might not be obvious, but I think this equation in purple will be easier to differentiate than this original equation that we're given up here. Let's see if that works out. Let's take the derivative of both sides of the equation. On the left-hand side, you might recognize that you have two different terms because of this plus, and each of the terms have a coefficient, a 2 and a 3 respectively. So maybe you'd be comfortable with me writing 2 times the derivative of the natural log of x plus 3 times the derivative of the natural log of y. And on the right side of the equation, I got the derivative of x times y. The natural log of x is just 1 over x, so my first term becomes 2 times 1 over x. The derivative of natural log of y, it might not look like it, but there's a chain rule going on there. Taking the derivative of the natural log part gives me 1 divided by y, but then I'm not done. I have to multiply that by the derivative of y because, again, y is a function. So think function composition here, even though it's not obvious at all. On the right side, I got something times something, think product rule. Got the derivative of the x times the y plus the derivative of the y times the x. I'm just about done with all my calculus. Let's see, over here I can clean this up and call it 2 over x. Over here, the derivative of y is y prime. So I can clean up this term by calling it 3y prime divided by y. I'm going to set that equal to, the derivative of x is just equal to 1, and 1 times y is just y. And then over here, the derivative of y is y prime, and y prime times x, I could write that as xy prime. I got 4 terms. 2 of those terms have y primes in them. I'll collect all the y primes on one side, and that'll allow me to solve for y prime. If you want, you could do that immediately, but if the fractions bother you a little bit, you could multiply both sides of the equation by x times y. If I multiplied this side of the equation by x times y, I'd have 2xy divided by x, and I cancel out the x's to get 2y. Over here, I'd have 3xy y prime over y, and I could cancel out the y's to get 3xy prime. Then over here, since I'm multiplying y by xy, I got xy squared. And then over here, since I'm multiplying xy prime by xy, I got x squared y prime. That's kind of an optional step. You didn't have to do that, but the nice thing about what I have now is it doesn't have any fractions, so that'll make it a little bit easier to collect all the terms with y primes in them on one side. On the left, I'd end up with 3xy prime minus x squared y prime. And on the right, I'd end up with xy squared minus 2y. Factoring out a y prime from the stuff on the left leaves me with 3x minus x squared y. And when I divide both sides of the equation by that stuff in the parentheses, I get y prime equals xy squared minus 2y divided by 3x minus x squared y. A couple of comments here. The reason we did this whole log thing was supposedly to make the calculus easier. Was the calculus in purple any easier than the calculus in red? I kind of think it was, but I don't know if that necessarily makes this process easier than the process in red, because we had to do all this algebra kind of up front. Our trade-off was more algebra in the form of log rules allowed our calculus to be a little bit more straightforward. Whether purple was necessarily easier than red is sort of a personal preference kind of thing. The other comment that I want to make is if you compare these two answers, they don't look like they're the same. I mean, there's some similarities going on in that both of them are a quotient of differences, something minus something on the top and the bottom. And there's some commonality in the coefficients. There's this 3 here and this 3 here and a 2 here and a 2 here. But really, big picture, they don't look all that similar. Why am I getting different answers? You're not. The difference between red and purple comes from the fact that x's and y's are related to each other by this equation. X squared y cubed is the same as e to the xy power is what this equation is telling us. If I multiply both sides of this equation by y, for example, I would get that x squared y to the fourth is the same as y times e to the xy power. Why am I making that observation? Well, y times e raised up to the xy power is something that shows up in this answer right here. So because this equation tells me that y e to the xy is the same as x squared y to the fourth, I could replace this entire term with x squared y to the fourth. And maybe if I replace this term with x squared y to the fourth and replace this term by doing some kind of similar analysis and then factored stuff out and canceled really carefully, maybe it's plausible to see that I could change this answer in red into this answer in purple. The good news is you don't have to do any of that. I just wanted to explain why we didn't make any mistakes anywhere. We're not really getting different answers in red and purple. They just look different. And sort of the connection that proves that they're equal to each other is the original equation.